The lecture and concept we're exploring today comes directly from Richard Feynman's historic 1964 lecture series, The Character of Physical Law, delivered at Cornell University. In this lecture, Feynman addressed a question that strikes at the very foundation of science itself. He explained how two completely different theories, built on entirely different ideas, can produce exactly the same predictions, and why science may never be able to tell which one is truly right. Feynman began by asking his audience to imagine two separate theories. He described them simply as Theory A and Theory B. He explained that these two theories could be completely different in their internal structure. They could be based on entirely different ideas. They could create completely different mental pictures of how reality works. One theory might describe reality in one conceptual framework, while the other describes it in a completely different framework. Psychologically, they would feel different. Intellectually, they would appear unrelated. To the human mind, they would look like competing explanations of the universe. But then Feynman explained something deeply unsettling. He said that when you actually use both theories to calculate measurable consequences, they produce exactly the same results. Every prediction that Theory A makes, Theory B also makes. Every experimental outcome that agrees with one theory also agrees with the other. There is no difference in their observable consequences. He emphasized that mathematically, it is often possible to prove this equivalence by analyzing the logical structure of both theories. Physicists can demonstrate that every prediction derived from one theory corresponds perfectly to a prediction derived from the other. This creates a profound situation, because science operates by comparing predictions with experiment. Science does not judge theories based on how intuitive they feel. Science does not judge theories based on how satisfying their explanations are. Science judges theories based on whether their predictions match reality. So, if two theories produce identical predictions, science has no way to distinguish between them. Feynman made this point very clearly. He explained that in such a case, there is no experiment that can tell you which theory is right. Both theories agree with experiment equally well. Both theories successfully describe reality. From the standpoint of science, they are equally valid. This leads to a conclusion that challenges the way many people think about scientific truth. It means that science does not always give you a single unique description of reality. Sometimes, science allows multiple different descriptions that all work equally well. But Feynman did not stop there. He explained that although these theories are scientifically equivalent, they are not psychologically equivalent. This distinction is essential. He explained that theories are not only used to calculate numbers, they are also used to guide thinking. They shape how physicists imagine the structure of reality. They shape how physicists generate new ideas. When a physicist works within a theory, they are not simply performing calculations. They are operating inside a conceptual framework. That framework influences how they think about possible changes to the theory. One theoretical framework might make certain modifications appear obvious and natural. Another equivalent framework might make those same modifications appear extremely complicated or unnatural. Feynman emphasized that even though the two theories produce identical results in their current form, the process of modifying them may be very different. A small conceptual change in theory A might be simple and intuitive, but finding the equivalent change in theory B might be extremely difficult. The mathematical transformation required might be complicated and obscure. This means that even though the theories are equivalent in their present form, they are not equally useful for discovering new theories. One theory might make progress easier. The other might make progress harder. This reveals something important about the nature of scientific creativity. Scientific progress does not come only from calculation. It comes from insight. It comes from recognizing patterns. It comes from imagining new possibilities. The structure of a theory influences how easily those possibilities can be seen. Feynman explained that this is why experienced theoretical physicists do not rely on a single representation of reality. Instead, they maintain multiple representations of the same physical law in their minds simultaneously. He explained that a skilled theoretical physicist might know 6 or 7 different theoretical formulations that all describe exactly the same physics. They understand that these formulations are mathematically equivalent. They understand that no experiment can distinguish between them. Yet they continue to use all of them. Not because one is more correct than the others, but because each one provides a different way of thinking. Each representation highlights different features of the system. Each representation makes certain patterns more visible. Each representation makes certain theoretical possibilities easier to imagine. By maintaining multiple frameworks, physicists increase their ability to generate new ideas. They increase their ability to discover new laws. Feynman then addressed another related issue. He explained that when scientists talk about the philosophical meaning of a theory, they are often referring to the conceptual framework that helps them understand its consequences. These philosophical ideas are not separate from the mathematics. They are ways of organizing the mathematics mentally. They help scientists think more effectively. He gave an important historical example involving Newton's theory of gravity. Newton's theory was extraordinarily successful. It explained the motion of planets with remarkable precision. It predicted their behavior accurately. For centuries, it appeared to be a complete and perfect description of gravitational motion. But eventually, scientists discovered a small discrepancy. The orbit of Mercury did not match Newton's predictions exactly. The difference was extremely small, but it was real. Feynman explained that correcting this tiny discrepancy did not require a small adjustment. It required a completely new theory. Einstein's theory of gravity replaced Newton's theory. But Einstein did not simply modify Newton's equations. He introduced an entirely different conceptual structure. Newton described gravity as a force acting between objects across space. Einstein described gravity as a curvature of spacetime itself. This was not a minor philosophical change. It was a completely different way of understanding reality. Feynman emphasized that both theories were internally consistent. Both were logically complete. But producing even a small difference in prediction required a completely different theoretical foundation. This showed that precise theories cannot always be slightly adjusted. Sometimes, they must be replaced by entirely new conceptual systems. This reveals that the philosophical structure of a theory plays a fundamental role in how it describes reality. It determines how scientists think about the universe. It determines how they discover new laws. And it determines how scientific progress becomes possible. Feynman then introduced an even deeper question. He addressed the role of what scientists often call philosophy or understanding. in relation to physical theories. He explained that when physicists talk about understanding a law of nature, they are not referring to something mystical or abstract. They are referring to a way of organizing the law in their mind so they can quickly see its consequences. Understanding is not separate from calculation. It is a mental structure that makes calculation more powerful. It allows a scientist to see what will happen without having to compute every detail from scratch. Feynman explained that these philosophical frameworks are not just words. They are practical tools. They help scientists guess new theories. They help scientists explore possibilities that are not immediately obvious from the equations alone. However, he also acknowledged that some scientists take a different position. They argue that philosophy does not matter at all. They argue that the only thing that matters is finding equations that agree with experiment. From this perspective, it does not matter how you interpret the equations. It does not matter what mental picture you use. The only thing that matters is whether the predictions are correct. Feynman explained that this view is both correct and incomplete. It is correct in the sense that agreement with experiment is the ultimate test of any theory. If a theory does not match experiment, it must be rejected, regardless of how beautiful or satisfying it may seem. But this view is incomplete because it ignores the role of understanding in discovering new theories. Equations do not appear automatically. They must be guessed. They must be constructed. They must be discovered. And philosophy often guides that discovery. To illustrate this point, Feynman presented a powerful historical example involving ancient Mayan astronomers. He explained that the Mayans were able to predict astronomical events with extraordinary accuracy. They could predict eclipses. They could predict the positions of the moon and planets. Their predictions were precise and reliable. But the way they achieved this accuracy was very different from modern physics. They did not have a conceptual model of planets moving through space. They did not imagine planets as physical objects governed by forces. Instead, they relied on arithmetic patterns. They observed cycles. They recorded numbers. They performed calculations based on repeating sequences. They could predict when an eclipse would occur, but they did not explain why it occurred. Their system was extremely effective at prediction, but it did not provide a deeper understanding of the underlying mechanism. Feynman then asked his audience to imagine a young astronomer living within that Mayan civilization. Suppose this young astronomer proposed a new idea. Suppose he suggested that the moon and planets were not just patterns in numbers, but physical objects moving through space. Suppose he proposed that their motion could be explained using a different conceptual framework. At first, his theory might not produce predictions as accurate as the existing arithmetic system. His theory might still be incomplete. It might still need refinement. The older astronomers would immediately challenge him. They would ask him to calculate an eclipse using his new theory. They would compare his prediction to their own. If his prediction was less accurate, they would reject his theory. They would argue that their existing system was superior because it produced more precise results. Feynman explained that this reaction would be understandable, but it would also be dangerous. Because new theories often begin in an incomplete form. They may initially produce less accurate predictions, but they may contain deeper insights that allow them to eventually surpass the old system completely. If scientists focus only on immediate predictive accuracy, they may reject theories that have the potential to produce revolutionary breakthroughs. This illustrates an important tension within science. Prediction is essential, but understanding is also essential. Prediction allows us to test theories. Understanding allows us to create new theories. Without prediction, science loses its connection to reality. Without understanding, science loses its ability to progress. Feynman emphasized that philosophy and conceptual frameworks play a crucial role in scientific discovery because they influence how scientists imagine possible modifications to existing theories. A conceptual framework may suggest new possibilities that are not obvious from the equations alone. It may guide intuition. It may reveal patterns that would otherwise remain hidden. This is why physicists do not treat theories as final truths. They treat them as tools. Each theory is a way of organizing experience. Each theory is a structure that allows the mind to navigate reality. But no theory is guaranteed to be ultimate description of nature. Feynman made it clear that multiple different theoretical frameworks can describe the same physical phenomena equally well. Science does not necessarily provide a single unique picture of reality. Instead, it provides models. These models are judged by their ability to predict experimental outcomes. But beyond prediction, the usefulness of a model also depends on how effectively it helps scientists discover new models. This means that scientific theories serve two purposes. They describe reality, and they guide discovery. Some theories are better at prediction. Some theories are better at generating new ideas. The most powerful theories do both. Feynman emphasized that physicists keep multiple theoretical frameworks in their minds because each framework offers a different way of seeing. Each framework reveals different possibilities. Each framework expands the range of ideas that scientists can explore. This flexibility is essential for scientific progress because the universe does not guarantee that reality will conform to any single human way of thinking. Scientists must remain open to multiple perspectives. They must be willing to abandon familiar ideas when new evidence requires it. They must be willing to construct entirely new conceptual systems when existing systems are no longer sufficient. Feynman's message was clear. Science is not a search for a final, permanent explanation. It is a continuous process of building models that describe reality with increasing accuracy. These models are not absolute truths. They are tools that allow us to navigate the structure of the universe, and sometimes different tools can work equally well, but each tool offers a different path forward. Each tool opens different doors, and the future of discovery depends on the ability to explore all of them.